Welcome to the Deep Dive.
Great to be here.
Today, we're going to dive into some sources about a concept you might use all the time, maybe without putting name to it. It's called the unitary method.
That's right.
And our mission really is just to unpack what it's all about, the core principles, and, see how it works for solving actual problems, simple ones, tricky ones.
Exactly. And at its heart, the unitary method is, well, it's beautifully simple, really. It's all about figuring out the value of one. Just one single unit first.
Okay, why one?
Because once you know what one costs or how long one takes or whatever it is,
Yep.
that's your baseline. You can then easily scale it up or scale it down to find the value for, well, any number you need. It just gives you a clear path.
Right, a starting point. Okay, so scaling. The sources jump right into two key ideas there, don't they? Talk about how quantities relate.
Direct variation and inverse variation. Crucial difference.
Direct variation feels pretty obvious, doesn't it? Like, more of this means more of that.
Absolutely. That's direct variation. One quantity goes up, the other goes up proportionally, and down together, too. The sources talk about cost and quantity. Classic example.
Sure. More apples, more cost.
Exactly. So if you know the price for, say, 5 apples, the unitary method says first find the price of 1 apple.
Okay, so you divide the total cost by 5.
Right. You divide. Then if you want 12 apples, you just multiply that single apple price by 12.
Got it.
Or, flip side, if you have a budget, say $10, and you know the price per apple, you divide the $10 by the unit price to see how many apples you can get. The ratio stays the same.
Okay, that makes total sense. Quantities move together. But then there's the other one. Inverse variation.
Yes.
That's the one that can sometimes mess with your head a bit, right?
Yeah.
Because it's flipped. More of one thing means less of the other.
Precisely. Inverse variation. Increase one thing, the other decreases. The sources use that classic example, workers and time to do a job.
Yeah, I remember that one.
Think about it. If 7 workers take 560 days for a job, what happens if you double the workers?
Oh, the time gets shorter, like halved.
Exactly. It halves. It doesn't double. So using the unitary method here is different. To find out how long one worker would take, well, fewer workers mean more time, right?
Right. A lot more time for just one person.
So you don't divide the time by the workers, you actually multiply. 1 worker takes 7 times longer than 7 workers.
Okay. So you multiply to find the 1 unit value in this case. 7 times 560 days.
Yeah.
That's the total worker days needed.
You got it. That's the total effort. Once you have that big number, the time for 1 worker, then you can figure out the time for any other number of workers. You just divide that total 1 worker time by the new number of workers.
Okay, I see. So the find one idea is still key, but how you find it flips. Direct variation. Divide to find one, multiply to scale.
Yeah.
Inverse variation. Multiply to find one, divide to scale.
That's the core distinction. You have to know which relationship you're dealing with.
And the sources push this further, right? Into like more complex stuff.
Oh, yeah. They talk about situations with, say, men and women working at different speeds, or food supplies for a group whose size changes.
How does the method handle that?
It's about breaking it down. You might need to find an equivalence first. Like, okay, if one man does the work of, say, 1.5 women, you convert everyone to a single unit type.
Like convert everything into man days or woman days or something.
Exactly. Get a common unit of work. Then you apply the inverse variation logic, usually inverse for work problems, to figure out the time or resources needed.
Interesting. They also mentioned something called the arrow method. Quickly, what was that?
Yeah, it's more of a visual aid, really. A way to line up the quantities in those multi-step problems. You draw arrows, basically, to show if the link between 2 quantities is direct or inverse.
Like a flowchart?
Kind of. It just helps you track whether you should be multiplying or dividing at each step, especially when things get complicated with different units changing. Keeps the logic straight.
Okay. So, pulling it all together, the big takeaway seems to be unitary method means always find the value of 1 first. That's the golden rule.
Absolutely. Reduce to the unit.
But the crucial next step is spotting whether things change directly together or inversely, 1 up, 1 down, because that tells you how to use that 1 unit value.
Precisely. Understanding the relationship is just as important as the calculation itself. It's a framework, really. Deconstruct the problem, find the unit, understand the relationship, then scale. Works for simple costs, complex work rates, all sorts.
And it's funny when you think about it, how often we probably do use this without, consciously labeling it, like scaling a recipe, or figuring, okay, if I help my friend paint, it'll take half the time, or estimating materials.
That's all a unitary method in action. Implicitly maybe, but it's there.
So here's something maybe for you, the listener, to think about. Beyond those everyday estimates, how could consciously using this method, really thinking, is this direct or inverse, help you tackle problems you usually find, well, a bit daunting?
Yeah, where could that structured thinking make a difference?
Something to chew on. We'll leave it there for this deep dive.